with me? All right, so question number 1. It says below are the number of K-12 schools for several states in the Midwest, between 2014 and 2015 school year. Now we want to use this particular data, right, from the NCES to find the standard form, right? So we're going to write a per capita in standard form and then do that in scientific notations, right? Now we know that when we talk about standard form, that's the original state of numbers. So for instance, this is numbers in standard form. All right. And then this decimal, if I write this decimal, this is also in standard form. Is that okay? Now we're going to write the per capita in standard form and then change them into scientific notation. We already learned that to write a number in scientific notation, move the decimal point such that there's one non-zero number in front of the decimal point, multiplied by 10, and then the exponent of 10 will be the number of times you move the decimal point. All right, you remember we said when you move the decimal point to the left, the exponent assumes a positive number, and then when you move to the right, you are actually decreasing the power of 10. Is that okay? So that's basically what we are going to be doing here. So here on this table, we have the number of K-12 schools in Indiana, Illinois, Kentucky, and Michigan. So for Illinois, right? So what we're going to do is that per capita means per person, right? Per person. So what we're going to do is that we are going to divide the number of K-12 schools in each state by the population, all right? So per person is, we're going to do 295 divided by 6.6, and don't forget this is in millions, right? The population is in millions, so we're going to do 10 times 10, 6.6 times 10 exponent 6 power. All right, so put that in your calc, compute that. Now for Illinois, we're going to do 859 over 12.9 times 10 to the 6th power, because all these are in millions. Right, we're going to do the same thing for that for Kentucky. 4.4 times 10 exponent that. Then here we'll do 548, right, over 9.9 times 10 exponent 6. Now, get your calc ready and compute each of the following. Is that okay? So when you compute that for Indiana, you notice that this is, and I've said that due to the 6 decimal places. All right, so this is going to give you 0.1, 2, 3, 4, 4 zeros and 4 5. Okay, now when you compute this, this is going to give you 0. Come on. This will give you 0.0000, and this will give you 6 places, right? And Kentucky is going to give you 0.000039, and Michigan is going to give you 0.000055. Is that okay? So this is the result you get in standard form for each of these states. Now you are going to write these in scientific notation. So against Indiana, so for this, for scientific notation, move the decimal point so that there's one non-zero number. So you're going to move the decimal point to the right, right? So 1, 2, 3, 4, 5. So this is going to give us 4.5, and then multiply by 10. And the number of times you moved, because we moved to the right, this will assume a negative exponent. We're going to do the same thing for Illinois. 1, 2, 3, 4, 5. So this will be what? 6.7 times 10 exponent negative 5. All right, Kentucky, 1, 2, 3, 4, 5, right? So 3.9 times 10 exponent negative 5. Okay, are you good? All right. Now let's go to Michigan. The Michigan is also 1, 2, 3, 4, 5, right? So this is 5.5 times 10 exponent negative 15. And you have completed the table successfully. Does it make sense? So per capita means per person. So anytime you have to do with per capita, divide by the population. Is that okay? And write your answer. Now, so you notice that here, each of these values represent per capita values. So these are per person, right? And these are also per capita values in scientific notation. So what this means is that here, when you come to the next part, we are going to take only the state of Indiana, right? And write the number of school districts for Indiana. So we actually, I should have indicated that we're going to write a number of school districts per capita, right? Per 1,000, per 10,000, and then per 100,000. So because this value, what we got for Indiana is 0.000045. This is per person. So if you wanted to interpret this statement, this means that there were 0.00045 school districts per person in Indiana. Is that okay? So that's what this represents. Now, if you want to do per 10,000, what this means is that we are going to multiply this by 10,000 and that by 10,000. Is that okay? So this will give us what? So literally we are moving 5 times to the right. So 1, 2, 3, 4, 5. So this is 4.5 over 10,000. So you explain that, you interpret that as there were 4.5 school districts per 10,000 people in Indiana. So this is it. So this answer gives you 4.5. Okay. So that's how you interpret it. There were 4.5 school districts per 10,000 people in Indiana. So basically what you're doing, you are multiplying by these. So you take this number and then you multiply by each of these, this number, and you multiply by that. So 0.000045 by 100,000. What will you get for that? So by 100,000 is going to give you, sorry, what did I do earlier? I was supposed to do 1, 2, 3, 4. Sorry, so we were supposed to multiply this by 10,000. So that is 4 places and not 5. So this will be 0.45. Sorry about that. So this is 0.45 instead. So when you multiply this by 10,000, that should give you 0.45. And you're going to take the same number here and multiply by 100,000, and that'll give you 4.5. So the interpretation is that there were 4.5 school districts per 100,000 in Indiana between the school year 2014 and 2015. So we're going to take this same number and multiply by 100,000, and this is what? 45. Okay, so that's exactly what you do when you're asked to write a number per any number. You just multiply the number in question by the number that goes with the per. Is that okay? So that's exactly what you do for these. All right. Now let's look at question number 2. Now for question number 2, it says if 12,345 cubic feet per second of water was released during a flood, how much was released after a week? So you know that 12,345, and you're talking about cubic feet, and this is per 1 sec, okay? Now, what you're going to do is you want to find per week how much was released per week. So really, you have to go to from seconds into minutes, hours, and then hours into what? Into days, and then finally into weeks. So we're going to use dimensional analysis. So you ask yourself how we're going to do how much water was released per minute. All right, and we know that 60 seconds is what? 1 minute. All right, so the goal is to change this. So seconds will take care of seconds. So this gives you how much of the water was released per minute. Now that's not what your goal, right? You want to move forward. So now you look at 60 minutes make an hour, right? So 60 minutes make an hour. So now minutes will take care of minute. So up to this point, you have how much of the water was released per hour. Now that's not your goal. Your goal is to get to weeks. So 24 hours in one day, right? Now hours will take care of hours. Now you have to go further and look at there are 7 days in 1 week. So days will take care of days. So now you have that per week. Now that should be the end. So therefore you just need to multiply the numerator. So 12,345 multiplied by 60 by 60 by 24 by 7. All right, divided by 1 times 1 times 1 times 1 times 1, right? So basically that is 7,466. It's actually a billion, 256, and then 3 zeros. All right, and that is what? In cubic feet per week. So this is the amount of water that was released per week. So it's actually 7,466,256,000 cubic feet per week of the water was released. Okay, nice. Now, question number 3. All right, and here you'll be allowed to use the formula sheet. Now, if you want to know the number of a kilogram is what times as large as a decigram. So let me share this formula sheet with you and show you how to do that. All right, the answer here should be 10,000, but how did I come by that? So you remember when we were looking at how to use the formula sheet. So here, what you see here, we have a kilo, right? Right, so this is a metric relations. We have a kilo, we want to move to deci. So kilo is right here. So we move 1, 2, 3, and 4. All right, because we have a kilo, which is 1, right? So every step we move will take a 0. Every step we move will take a 0. So therefore we have 1 and 4 zeros, and that is what? 10,000. Okay, nice. So that is the answer for question number 3. So that's as simple as that. So we have 10,000. So a kilo is 10,000 times as large as a decigram. Okay, nice. Now let's look at number 4. And you can use the same conversion sheet, all right, to do that. Now you have 120 pounds. You want to change to a kilogram, okay? So you know that 1 pound and a pound will go to the bottom because you have a pound on top so that they will take care of each other. This is 0.4536 kg. That's the identity ratio, right? So this will take care of that, right? So 120 times 4536 kg, and that gives you what? 54.4 kilograms, right? It depends on how many you want, how many places you want to round to, all right? If you want to do 2 places, that will be 54.43, but I'll specify on the exam or on a test or even on a quiz, right? All right. Now, so that's for question number 4. Does that make sense? Are you good with that? All right, nice. Now let's look at number 5. So a bullet train travels 100 miles per minute, per 100 miles in 10 minutes. We want to find the speed in miles per hour. Is that okay? So we are originally we're doing 100 miles per 10 minutes. So that's the speed of the bullet train, right? Now speed is what? Distance over time taken. So we want to change. So our goal here is to change 10 minutes into hours. Is that okay? So we know that 60 minutes is an hour. So 60 minutes is an hour. So we're going to multiply that by that. Now minutes will take care of minutes. And our answer, we know that this will take care of that. So what do we have? We have 600 miles per hour. Is that okay? So that's the speed of the bullet train that travels 100 miles in 10 minutes. So that's the speed of it in hours. So the bullet train travels 600 miles in an hour. Is that okay? All right, good. So that is for number 5. Now let's go to number 6. Now number 6, we want to find the absolute and relative change. So there were about 3.6 million babies born in the US in the year 2020, according to the US National Center for Health Statistics. Now, according to the report, it is the lowest since 1979. So you notice there are going to be some redundant information here. Now, in 2019, 3.75 million babies were born. We want to answer the following questions. Right. So we know that absolute change is what? The new minus the old. Is that okay? So between 2019 and 2020. So the data point that goes with 2019 is our old, right? And the data point that goes with 2020 is our new. All right. So we have 3.6 million for the new, and then we have 3.75 million for the old. Is that okay? Now this is going to give us 0.15 million, and 0.15 million is about basically that's about, and this is actually a negative answer, right? And this is negative 150,000. That okay? So that is how that should be, all right, for the absolute change. Now for the relative change, we know that relative change is the new minus the old over the old. Is that okay? Now, and we know that because it's the new minus the old over the old, the new minus the old is the absolute. So we could decide to divide the absolute, right, by the old, which is 3.75 million. Is that okay? You could actually write this in full to see the full effect of it. So this is 300, that's right. If you do that division, that should give you about 4%. All right, whatever you get here, you multiply by 100 to get that in percentage. And that is 4%, and that's negative. Is that good? All right, now let's go to C. For C, we want to find, and let me clear this off. For C, we want to find the birth rate for 2020 per minute. So for 2020, we have the birth rate per year. Now we want to do the birth rate per minute. So we know that 3.6 million, okay, is the birth rate for the year. Now we want to change year into seconds. So basically into minutes. How many minutes are there in a year? So that's the step that we're going to do. Is that okay? So we will do 36 million divided by, after changing the years, how many minutes are there in a year, we divide and get the birth rate for 2020 per minute. So we'll do the dimensional analysis. Now you ask, you can actually go from weeks. Now there are 52 weeks in 1 year, right? So we have 1 year, we have the 52 weeks. Now this takes care of that. So we know the birth rate per week, but that's not our goal. We have to do second. So we'll go again and do 1 week. All right, how many days? We know that for 1 week, there are 7 days. And we do not end there. We know that. So this is because we want this to take care of that. Now, we do 1 day, we have 24 hours in a day, right? So 24 hours, and then we have that hours right there. But we want to get into what? Minutes. All right, and then we know that 1 hour has 60 minutes, so that hours can take care of hours. So at the end of the day, we are going to do 3.6 million divided by 52 by 7 by 24 by 60. Okay, now if you do that division, that should give you about 6.9, but we are talking about a number of babies, so it's better we talk about a whole number. So that is about 7 births or 7 babies per minute. All right, so the birth rate in 2020 per minute is 7 babies or 7 births per minute. All right, so that's what happened in 2020. Are you good with that? All right, good. Now let's go to number 7. So for number 7, it says a certain drug dosage calls for 25 milligrams per kilogram per day and must be administered every 6 hours. All right, now if it must be administered every 6 hours and there are 24 hours in a day, that means that it's divided into 4 doses, right? Now, if a person weighs 250 pounds, how much of the drug should be administered per week? Is that okay? Now I'm going to focus here first. So what this means is that 25 milligrams per kilogram. And since we know that medication is administered based on the weight of the person, what this means is if the person weighs 1 kilogram, give 25 milligrams of the medication to the person per day. Is that okay? So if a person weighs 1 kg, give 25 milligrams of the medication to the person per day. That means that if a person weighs 2 kilograms, you have to give 50 milligrams of the medication to the person per day. If the person weighs 3 kilograms, you're going to give 75 milligrams of the medication to the person per day. Is that okay? Now, but the person we are talking about here weighs in pounds. So to conform, we need to change 250 pounds into kilograms, all right, to be able to tell how much of the medication should be given to the person. So we're going to change 250 pounds, okay, into kilograms, all right, and then we know that 1 pound is 0.4536 kg. All right, so that would change the weight of the person into kilograms. Now, when you do that, you multiply by 25 milligrams per kg, right? And that will tell you how much of the medication you should give to the person. Is that okay? So you multiply the weight of the person by the volume that you're supposed to give. Now, that does not end there, right? We don't end here because, so this is going to give us how much volume of the medication we're supposed to give. No, weight, sorry, milligram is weight. So how much weight of the medication should be given to the person per day? So this is 2835 milligrams, okay, per, and this is per day. Is that okay? So milligrams is weight. I kept saying volume, but milligram is weight. So that is how you do it. So this gives you how much per day. That the question is, we should find how much of the drug should be administered per week. Okay, so if you want to do that, what do we do? So you notice that we have to change this. All right, now we know that 7 days a week. So therefore, days will take care of days. So literally, basically, we are multiplying the volume per day by 7 to know how much, all right, should be administered in a week. And this should give you 19845 milligrams per week. All right, so that's how much of the medication needs to be administered per week. Is that good? All right, so that's basically how you find that. Is that okay? So you notice there was some redundant information. Must be administered every 6 hours. So if you are thinking you are going to divide by 6 hours, we didn't really need that, right? Because we just want to find how much of the medication should be administered per week, and that did not really play any role in getting that out. Okay, nice. So now let's go to question number 8. Okay, question number 8. Now for question number 8, we're going to use this table to do that. Okay, so this talks about currency conversions, and you notice that I've done US to foreign, right? And foreign to the US dollars. Now, we want to look at the first rule, right, for euro, and write two identity ratios that can be used to do the conversions. And here it's very simple. So here, let me create some space here. So now you look at the table closely, and this is US to foreign. Is that okay? So what this means is that we have US on top and then foreign at the bottom. So what this means is for the first identity ratio, we're going to do 1.1. Okay, so that is in US dollars to 388. All right, and that is in US dollars, so I wouldn't. And then this is 1 euro. So that's the first identity ratio. Okay, and then the second identity ratio you need here is that you use the second one. All right, so this is how many euros per dollars, and that is what. So euro, this is the symbol for euro. So 0.0.890958 euros for every 1 US dollars. Okay, so these are the two main identity ratios you could generate from there. Are you good with that? Now for B, it says you visited your friend in London, all right, and then you take $500. You want to know how many euros would that be? You want to change $500 into euros, okay? So what identity ratio are you going to use here? So you notice that you really need to go with this one because you have, which one will you go with? So this is 0.890958, and then you have your one USD right there. So that USD will take care of the USD. Now your earn will be in what? In euros. And that should give you this amount of euros, 445.48 euros. Okay, nice. Now, when you were leaving London, you have 350 euros. Now you want to change the euros into dollars. So you have 350 euros that you want to change into dollars. So this time you use the other identity ratio, right? So you know that we have one USD here, 1.1222388, and that is USD. And then you know that is what? 1 euro. Now euro takes care of euros and your earnings will be in dollars. So this time this is going to give you 392.84. Okay. And that is how much dollars you bring home. Okay. Now on a different trip to Cancun, you return with 2,000 pesos, right? How much are those worth in dollars? So you have 2,000 pesos, 2,000 pesos or pesos. I confuse that all the time. Now, what's the exchange rate? So you're talking about this guy right here, the pesos. So, you know, one USD is what? So actually, we're supposed to have USD on top. So the pesos should go here. So you have one pesos up here. And then you have 0.054058 USD right there. So pesos take care of each other, and your answer is what? 108 and 12 cents. So $108.12. Okay, and that's how much you have in dollars. Does that make sense? Okay, so this should give you some clarity. So US to foreign. So that means that US should be on top of your ratio, and then the foreign currency should be at the bottom, right? And then here, foreign to USD, that means that the foreign currency must be on top, and then the USD must be at the bottom. Okay, so those are the two identity ratios that you can generate, and you use that for your calculations. Now, this is expected to be a bonus question that I'll answer them for you here in a bit. Now, we have this problem that says that assume when you take a bath, right? So when you take a bath, what you do is that you fill the bathtub halfway, right? Now the tub measures 60 inches by 30 inches by 15. All right, because we're talking about space, we're talking about volume, right? So the first thing that we need to do here is to find the volume of the bathtub. So that is what? 60 inches by 30 inches multiplied by what? 15 inches, and that will give you the volume of the bathtub, and that will give you 27,000. And this is because we are doing inch by inch by inch, that will give you cubic inches. Okay. So that's the tap volume. Is that okay? Now, when you take your bath, you fill this tap, you don't fill this tap to the brim, or you don't fill it all the way up, right? You fill it halfway. All right. So that is the bath tap volume. So the bath volume. So this is actually the capacity of water that can fill the tap, right? But you fill it halfway. So to know how much water you use, you have to divide this by what? By 2. That will give you the halfway volume, okay? And that is what? 13,500 cubic inches. So this is what you use for your bath. Is that okay? So 27,000 is the entire volume of the bathtub, right? But when you take your shower, because you fill it halfway, you have to divide 27,000 by 2. And that gives you the volume of water you use, right, to take your bath. Now, it says that when you take a shower, so we are looking at a shower and a bath. All right. Now, for shower, you use a shower with a flow rate of 7.5 gallons. So that is the flow rate. So your bathtub, your shower flows at 2.5 gallons per minute. So that means that for every minute, 2.5 gallons of water is dispensed out of the shower. Is that okay? So that's the flow rate of your shower. All right. And you typically shower for 12 minutes. So therefore, if you want to know the number of gallons of water for shower. So if you want to know how much you use for how many gallons of water you use for your shower, you have to do the flow rate, which is 2.5 gallons per minute. Okay. Multiplied by the 12 minutes that you take your shower. So that minute can take care of minute. And this will give you 30 gallons. So for your shower of 12 minutes, you are dispensing 30 gallons of water. Is that okay? Now, why are we doing this? We are doing this because the first question says, do you use more water taking a shower or a bath? So we know the number of gallons we are using for the shower. Now, to make a decisive decision as to whether we use more water for shower or for bath, we need to find the number of gallons of water we use for the bath, right? But we have this in cubic inches, so therefore we need to change this 13,500 inches into gallons. Is that okay? But we are already given that 7.5 gallons is 1 cubic foot. So we're going to change that into gallons. So we have 13,500 cubic inches. We will divide by 1 and multiply by. Now we have to, there's no direct relationship between inches and gallons. We have to go through feet, right? But we know that 1 foot is 12 inches. Now, because we are dealing with a cubic unit, we have to do 3 times of that. All right, 3 times. This is because we are doing a cubic unit, so that these, when multiplied, will take care of all that, and our answer will be in cubic feet. So this is going to give us 7.8125 cubic feet. All right, but that wouldn't be our final stop, because we want to compare, we want to change into gallons. We know that 1 cubic foot is what, 7.5 gallons. So we are going to multiply this, all right, because this is in gallons per 1 cubic foot, so that this will take care of that. And this is giving us 58.6 gallons. All right, so we have changed how many cubic inches of water is used for a bath, right, into gallons. So this is how much we use, how many gallons of water we use for um, bath, right? So you can say that, do you use more water in taking a shower or a bath? So you use more water taking a shower, a bath than a shower, right? So this is for bath, and this is for shower. All right, so that is how you've distinguished the two. Now, it says, how long would you need to shower in order to use as much water as you use taking a bath? Now that you know the volume of water or the gallons of water you use for a bath, just divide that by the flow rate. So we're going to do 58.6 gallons by the flow rate of what? 2.5 gallons per minute. And that will give us 23.44 minutes. Is that okay? So how long would you need to shower in order to use as much water? So if you shower for 23 minutes and change, right? You use the same water for a bath. And that's basically all that we need to uh, discuss for the review for exam number 2. Okay, so let me know if you have questions. I know it took a while, but it's worthwhile, right? So thank you so much, and reach out if you have any questions. Good luck. Bye.